Right, hi everyone. My name is Vlad. I'm a structural engineer with Arup. And today is week 8 and I'm going to be talking you through Karamba, which is a finite element package which is native to Grasshopper. And while I'm going through stuff, can you please go and download this file? Because that's a base file that we're going to need for the exercise later on. You're working fine? Yeah? Cool. So as I said, we are doing this week 8, and this is where it becomes more about structures. And just always referring back to this diagram as to why we are doing parametric engineering and what are the real benefits of doing engineering parametrically. So we started off in weeks 1 to 5 looking at boundary conditions. So if we're just looking at the problem from an engineering standpoint, weeks 1 to 5, we learn how to use Grasshopper, how to define geometry, using all the native functionalities and some plugins like Weaverbird and so on. So that most of the course is about that, getting to grips with Grasshopper. And then in week 6, Connor showed you form finding and some quite basic geometric optimizations using Kangaroo, which is a particle spring model. He did a 2D example of a funicular form finding, sort of an inverted hanging chain. And then looking at equal lengths optimizations and planarity. And this week, well, week 7 was Galapagos, which kind of could be applied anywhere. You could use Galapagos to optimize geometry, or you can use Galapagos with Kangaroo for form finding, or for geometric optimization. Week 8 is now when we start looking at structural analysis and structural optimization. As Andrew mentioned early on, the structural optimization part might not work for us today because there seems to be a license problem with Karamba. But I will run through the entire exercise, and at the end I'll show you on my machine, I'll show you what that part actually does, and then when we fix the license you can all do it in your own time. But essentially the reason why parametric engineering is useful is because we can close that loop. You can go through setting up a geometry, form finding if you need to, doing the analysis, the optimization, and then looping through that. Of course, it is useful if you only go one step at a time. Setting up parametric geometry is very useful if you have to do changes. Form finding by itself is very useful. Then you can throw it into another package like GSA, Abacus, or ANSYS, or anything else that could be that Grasshopper can export out to. But of course, if you can do the entire thing natively to Grasshopper, that has many advantages. And this is where Karamba comes in and is very useful. We use Karamba a lot for our projects for very early on. So, of course, no one is expecting people to be going to building control and submitting a set of calculations using Karamba. People might wonder what the hell that is. But when we're looking at very early on in the projects where we're designing with the architect and there are 1 million options on the table, it comes in very handy. And the reason for that is because it's native to Grasshopper. Everything is inside. Of course, there are other packages out there, and Paul Jeffries has developed Salamander, which is a package that links Grasshopper with other external packages like GSA, Ecotect, and Revit, and so on. Their interoperability packages, for example, Geometry Gym is similar to Salamander, whereas it connects Grasshopper to other analysis packages. And then there's Flux, which is a data exchanger, and so on. All of these plugins you can find on Food for Rhino and so on. And I recommend just exploring their functionality and see which one works best for you. So the example that we're going to do today is the same truss that you built in week 4, which is that Pratt truss. Quite simple setup, geometrically. So we're going to use the base file from week 4, which is the file that you should hopefully all have now. And the problem that we want to solve is if we have a span of X meters, we want to get from A to B, maybe it's a bridge. What is the lightest Pratt truss for a given fixed load that is going to do the job? And the boundary of the problem is it's made out of steel, and it's designed to Eurocode. And it has a deflection limit for a live load of span over 300. And I'll show you how we set all that up. Now we have another opportunity here to download the file, if you haven't done it yet. You all have it? It's good to go? And before we go into Rhino, I should just show you what the functionalities of Karamba are. It's basically a finite element package, which is native to Grasshopper, as I said. And it has everything you might expect from a reasonably basic FE package. So it's quite good with beam elements. It has a linear beam element, which you can use to solve linearly. Second order, you can do large deformation, so large strains, but only geometric, so it doesn't have material nonlinearity. You can do linear bifurcation analysis, which is the buckling, finding the mold shapes and the buckling factor for a load combination. And then the natural frequency of vibration. And it has a bunch of other fancier stuff for beams and for shells, which is optimizing typology. So you have a domain of beams or shells, you apply a load, and then you would add or remove elements to fit that load case. It has a cross-section optimizer, which is one of the functionalities we're going to be using today. And what that does is that for an internal force and moment of X, it finds what the member is from a library of cross-sections that would give you a utilization of 1. So it finds what is the lightest cross-section that will do the job for the internal forces that we have in the structure. And then tension compression eliminator, it's basically a setup. If you have a setup with truss elements where you would like to remove tension elements or compression elements for whatever reason, then it can do it for you automatically. And then everything else is pretty straightforward. You need to set up, like in any fine element model, you need to set up the geometry, then apply loads, supports, choose the material, choose the type of analysis you want to do, and then analyze, read the results, and post-process. So if we now jump into Rhino and open that file, you should all have this in front of you. It's the same example as week 4. So what do we have? We have we're defining a single point here with at the origin 0, 0 in the xy plane. The span is driven by a slider between 15 and 50 in this case. What that does is that translates a point from the original point by that distance, and it creates the bottom chord. We then have the depth, which moves the bottom chord by that distance. And then the two chords are divided by the number of bays, which is a slider here between 0 and 100. And then by connecting the intersection points of the top and the bottom chords, we create the verticals. I'm just going to have this. So yeah, so here are the verticals. And by shifting the list of the intersection points and connecting them appropriately, we get the diagonals. And if you select that last row of components, you see the truss that we have. So we have, as a user input, you have those three sliders at the beginning. And that's all you need to create a truss. So what we're going to do now is we're going to get into Karamba plugin. And first of all, we're going to set up the elements. So the way to do this is, as with any other finite element package, the moment you import the geometry, that's the point where you start introducing the elements and choosing what geometry becomes what type of finite element. So in this case, we only have lines. So we're going to turn the lines into beam elements. So to do this, you go in Karamba plugin, model, and line to beam. And we're going to take the left diagonal and plug it into line and the right diagonal. That'll be one family of elements. So we need another 4. We need one for the bottom chord, one for the top chord, and the verticals. So what is quite important with Karamba, especially when in this example it's reasonably simple because we're going to be using the same cross-section throughout, and then the optimizer will be selecting the right cross-section in the right place. But typically when you have different elements, the important thing is to name them correctly and then to keep that notation throughout the analysis. So we have in the beam ID, that input parameter here, in the line to beam component, we need to plug in a panel, and in that panel we can type in, so we have diagonals here. It's just a string input, diagonals, and we plug that into beam ID. So we need a few of those. So we have bottom chord, upper chord, I've called it here, and the verticals. So now Karamba has translated those those arrays of lines that we have from the geometry. It has translated them into beam elements. And that's all our element assembly for this model. So there's one thing we got to do in Karamba is to assemble each individual part of the model. So if you go into parameters, Karamba parameters, and choose the element component, then we can plug in the element output of each of the line element components, line to beam, into this assembly. And once the lines have been once the beams have been assembled, then we can use an overall model assembly and run the model. It's just a step that we have to do in Karamba. But before we can use this, we need to flatten the list, because now at the moment, if you look here, each one of those they're all flat lists. But when they come together, they come in as different sizes. So they're all different size arrays, different dimensions. So the way to fix that is to just flatten at the input. And now we have a flat list with 25 inputs. So this is very interesting. You can see how the beams are defined. They all have a name, and they have a starting coordinate and an end coordinate. So this is the element setup complete, and we can create a group for that. We can call this group elements. Everyone good? Following? So next up, we have to set up some supports for the truss. And in this example, the supports are reasonably important, but not very important. If you have an arch, the end conditions become more important. Nevertheless, if we only support the end of the bottom chord, the model is going to be unstable, and it would want to spin in a rigid way around the bottom chord. So ideally, we support the end 4 points. And to do this, we need one pin support, one roller, and 2 out-of-plane supports. And how to do this in Karamba? So first of all, we need to get our support component from model support. So as I said, we have 3 different conditions: pin, roller, and 2 out-of-plane. So let's copy this component 3 times. So the origin point, if we come back to our geometry setup, that origin point 0, 0, we can use this as our pin support. So we drag that coordinate into the position input of the support component. The default plane for the support. So the way this component works, it has 6 degrees of freedom, of course, for beam elements, 6 degrees of freedom, 3 translations and 3 rotations. So you can restrain by toggling these buttons. You can restrain the freedom in question. And it would work based on a defined plane. And it's always a local to that. It's always the support is local to that plane, so you can define any plane you wish. And in this case, let's define an XY plane. So you just double click on the canvas and type in XY. And that comes up with the XY plane component at origin 0. You can just plug that in into all the plane inputs of the support. So we already have our pin support. So we've got the 3 translations fixed on that node. Then the other point we need is the other end of the bottom chord, which comes out of this point B here, from that addition component. The output R should be plugged into here, into position on the second support component. And that restraint, so point A is restrained in 3 directions, point B, the other end, is restrained just in 2. And if we have our XYZ global coordinate system matched with the local coordinate system here, XY, we know that we need to restrain Z and Y. So TY and TZ. And now, how do we get the other 2 points, the other ends of the top chord? So the way to do this is to get all the top chord points, which are coming out of this component, the divide curve component in here, and the points output, we want to select the first and the last items from this list of points. So the way to do this is to type in item in the canvas and select list item. So this is an item selector from a list of data. We get the top points of the top chords. And just here, when you zoom in enough on that component, you can press the plus on the top, and that would come up with I and -1. So I is the first component, which is 0, and -1 is the last component. So these 2 outputs now are the coordinates, and you can see when you select that, it comes up on the screen. We just need to plug in this into the third support, and that the support condition there needs to be TY, just the translation in the Y direction, out of the plane of the truss. And then in a similar fashion, we need to assemble the supports, just like we did for the beams, for the line elements. So we go to Caramba, Parameters, Support, and then we plug all of these outputs from support in here. And again, flatten the list. What we have now, if you just hover over this component, you can see how Caramba actually defines it in the input file. We have 4 supports, the 4 coordinates, and the degrees of freedom that are restrained are either true or false. So you can see that there's more written that is not actually seen in the component, which is the restraint is for all load cases, and the displacements at those points are constrained to 0. So if you wanted to have a prescribed displacement, then that condition here, these lines will be altered to whatever displacement you wish to impose. So that's the supports setup complete. We can create the group here again. Call it supports. Now it will be good to set up some loads for the truss. Ideally, at the moment we're going to just set up 2 load cases, one for the self-weight, which is automatically calculated in the software, and the other one, we're just going to set up a live load, which is applied at the nodes of the truss. So if you go to Karamba load and just take the load component twice, and in the first one we just have gravity, so that can remain as it is. If you hover over the vector input, you can see that it's a unit vector in the vertical downwards direction. So that's already predefined, assuming that your model is defined in the XYZ plane with the Z being the vertical, all pointing upwards, which is typically what we do. And then the load case, if you hover over that, the load case is 0. So you can set up different load cases and call them different things. In this case, we're just going to have load case 0 and load case 1. So the second type of load we're going to have, as I said, is a point load. So from a drop-down menu in the second component, just choose point, and the component will change into, you would need to receive a lot more input. So we need to decide what live load to have on. If we just create a slider by double-clicking in the canvas between 1 and 100, and then add the multiplication component here, and let's multiply that slider value by the span of the truss. So one of the other sliders right at the beginning of the definition. And what that means is that now this slider has turned into load in kilonewtons per meter. And by changing this and multiplying it by the span, we have the total load applied to the truss. So now that we have a total load in kilonewtons, which in this case, in my case, is 33 times 45, so we have 1,485 kilonewtons altogether. We need to divide this by the number of points. So if I go back to the geometry definition, so in my case here I have 7 nodes. So I need to divide that by 7. But because I have set up the base parametrically, I would want to know how many points are there in the top chord. What is the number of divisions that I have? So I have 7 divisions, and if you just get the length, the list length component, you can find this in sets list length. And we can plug in that top chord divide curve output, the number of points in the top chord in here, and we get 7. That's in my case. So all we need to do now to get the load per point is to divide the overall load by the number of divisions. So if you just get the division component and divide one by the other, we get here 212 kilonewtons per point. So we can apply equal amount of load on each point. And of course we need to apply that as a vector. So you can apply any vector. In our case, we're just going to have a vertical downwards load. So this is positive at the moment. So in order to be downwards, we need a z vector downwards. So if I go negative in the canvas, that will just turn this number into negative, and then unit z vector. So now we've created our load vector, which is 0, 0, minus 212. So 212 kilonewtons vertically down. And now we can plug this into the force input in the loading component. The moments are 0. It's local. No, it's global. And the position where we apply this is all the points of the top chord. So we need to get, again, this is very popular output here, top chord points, gets plugged into position. And for the load case, we would have to change this because at the moment we have 2 load cases which are 0, which is fine, but it means that when it comes to reading the results, we won't be able to know how much of the force comes from, how much of the deflection or internal forces come from gravity, and how much come from this live load that we've applied separately. So all we need here is a panel with a value of 1. And now this is load case 1. So we need to assemble the load. So if you go into Caramba, parameters, load, same thing as before. I'm not quite sure why this is like this. I guess it's just to be able to tidy up the model. And we can create a group here called loads. So now we've set up the loads. There is couple of things missing. We need to set up the cross sections of the beam elements, the cross-sectional geometry. And the way you do that in Caramba is, if you go into the cross-section tab, you can select, in our case we're going to be selecting elements from the standard cross-sectional tables. So we're going to select the UK standard section, and all the cross-sectional properties are going to be read off a table automatically. So we choose the cross-section selector, and here we need to do a little tedious task of choosing which elements we apply which cross-section to. So all we need is a panel with all these strings typed in a numerical, in a string format. So we have upper court. And it's important here to use exactly the same notation as you've used for your element setup, even if they're different from what I'm doing here. Bottom chord, verticals and diagonals. And if you right-click on this panel component, and just select multi-line data, plug that in to name. Sorry, that's wrong. Plug it into element IDs. The name is the identifier from the cross-sectional library. So another thing we're going to need is the cross-section range selector. So get that component over. And if you click on select, it comes up with 3 drop-down menus. So we're going to choose UK, country, shapes, O, family, CHS, Celsius, let's say. And plug that in here. What actually, if you just put a panel up, what that component contains, it's a list of cross-sections, essentially, and all their corresponding cross-sectional properties, which you can't see in this table. So if we want to select just one cross-section, as we're building the model now, just have a panel up and type in 200, for example. You're going to see that I've just selected the CHS 610 by 14.3, and I've applied it to all the different parts of the truss, the upper chord, bottom chord, etc. You scroll down in that list to 200, that's the one we've selected. So as I said, this name input here is the index that's being selected from whatever list you have here of cross-sections. Now again, let's assemble the cross-sections. Just go cross-sections in the parameters, plug that in, flatten the list as before. And we can create another group here. So cross-sections. Yeah, so all that happened here is that we've selected the 610 CHS for all the elements, essentially. And later on, we're going to run the optimizer, which would basically loop through the entire list of cross-sections and choose one for each element, which will give us a utilization of 100% within a deflection limit that we're going to set. So the only thing now left before we can start running this analysis is the material setup. So that's the easiest one. Caramba, material selection. If you go in here and click on select, drop down menu, family steel, name, most common steel used these days, 355. And now we need to tell this material component which elements to apply this material to. So we can just copy this panel up there once with our 4 different material setups. So that applies still S355 to the 4 different materials, and then we can assemble parameters, material. No need to flatten the list, there's only one item in that list. So we can create a group called material, materials, and that completes the what's called the pre-processing of a finite element model. So we have the geometry, and then we have all the boundary conditions of a finite element model. And now we need to assemble all these things into one component which is called assemble model. So if you go to Karamba model, assemble model, essentially that just consolidates everything into one place. So we just drag all these individual assemblies. So the element one, the support, ordered in the right way, the loads, cross-sections, and materials. So you can see here there's some other inputs. You have joints. So what a joint in Karamba is an element release, which is also known in some other softwares, an element release. So if you have a beam connected to a beam without a release, then that means that all the degrees of freedom are coupled. You can choose a joint in Karamba to release some of those freedoms. So there are also sets of beams, and the limit distance is when the elements get collapsed if they're below a certain length. So for some of the functionalities that I'm not showing you today, the Karamba manual is very handy, and all the examples that are on the website. So if you start using Karamba after this, you can my advice is just go through all the examples one by one, starting from the easiest one to the hardest one. And then for whatever problem you have, just always refer to the manual. And it's actually quite a handy manual. And then if you get stuck past that point, email Karamba, and they'll provide you some support. That's sort of the way that I would approach a problem, rather than throwing everything in and something not working at some point, and it can get quite annoying. So you can work through that logic. So now that we have the model assembled, just go for algorithms. So Karamba algorithms. So algorithms is what most other software is called. So is the type of analysis that's going to get carried out. In our current version here, in this room, we have somewhat limited algorithms available. But for the first part of this exercise, we only need the linear solver. So we're going to go analyze theta 1, or also known as simple linear analysis, and plug that model in from model to model. We good? Okay. So after you've assembled the model output and the model input on every other component after that is quite an important thing to follow through. So now that we've input the assembled model into the solver, and this thing says here, this component run once, it means that the analysis has been run. We can have a look at some results. You can put a panel up here to check what the mass of the model is. In fact, what I usually do is you could just divide that by 1000 by right-clicking over mass and go into expression and type in x over 1000, and that'll give me the mass in tons. So Karamba is one important thing that I missed at the beginning. Is Karamba works in SI units generally, but not always. So some of the inputs are set up in a way that you can't change the units, and the only way to know what you're inputting is either it doesn't run very well, or just hover over things and it'll tell you what unit is expecting. So for example, here in the load component, if you just hover over force, it tells you input force vector kilonewtons. So if for whatever reason you had your units set up in newtons, which is the SI unit, then it wouldn't work. So watch out for this. It's kind of set up in a funny way. So here we go. We've got 28 tons for, well, in my case at least. You should have something meaningful if you're sort of anywhere along in the middle of these sliders. Check if that's the case. If not, let's fix it. So this is the sort of the analysis, the solver bit done, and we can call this group analysis. The interesting thing here is that we've been building quite a bit without actually seeing what's going on. So I'm afraid that's the way Karamba is. So you've got to have your geometry set up knowing that it's all kind of connected and it's fine. In any case, you run it, and if it doesn't work, you need to chase it back. But having it tidy, like I have it here, in a way that you can follow through and you know in a very simple linear way what follows after what, helps you debug stuff later on. Just because the Karamba setup is such that, for example, when you click on these elements, it actually gives you some points, which could be confusing. The supports are not even there when you click on them. So none of this pre-processing part of Karamba is visible. So when you go into the post-processing, you can see a lot, and it's very handy. So let's do some of this. You all got up to that point, okay? Right, so we have pre-processing, analysis, post-processing. So the way to do some post-processing in Karamba for beam elements is if you go Karamba results and go model view. It's a very handy component. And plug in model. So the model input here is a model that's not solved, and the model output from that analyze component is the sort of the output, the results. So if you just expand this component completely, it's quite a big one. And you can start seeing now some stuff. So in the display scales, you can display deformation, reactions, load, supports, etc., all to different scales. So the deformation is, you can just scroll and have a look at how the structure deforms. We still don't know what the magnitude is. That's something I'm going to show you how to do in a minute. What I found with reactions here in this particular example is that you have to go very small on the slider to be able to see these arrows and the magnitudes. So you can see here the reactions in kilonewtons. So obviously in this case all the reactions are just vertical. Everything else should be 0. The loads are shown as well with red arrows pointing down. You can scale the vectors and the support as well. Now you can finally see what the support, what directions you've supported those nodes in. So it should be all looking something like this on your screens. The local axis is something that is quite important when you have elements which are not linear, or when you want to align beams with shells and you're interested in having, for example, in a stiffened shell model where you have a 2D element model with beams running along the edges of shells to stiffen shells up, then it's important to know what the orientation of those beam elements is, and to be able to control it as well. So this tab here, the local axis, shows you x, y, z of each beam, with the x always being along the element, and then y and z. The best thing to do, and that's the case for any FE software, is to read the manual and see what the axis notation is for each element, and don't assume that they all follow the same thing. It's better to just know what the axes are for the model. Especially when models get complex, it's important to know basic things like this, so you don't make simple mistakes right at the beginning and then try to find the problem in a very complex geometry or something like that. And then the last one is joints. In this model we don't have joints. As I said, joints are just element releases, in other words. So we need another component. I mean, you could play around with this and see what these other tabs do for you. So we can put up the names of the materials, the cross sections, and as you change this parametrically, obviously all of this will change. So depending on what we need out of the model, you can see how we've defined the elements. So we've got all the bottom, top chords, and so on. The element names and the nodes, the element numbers and the node numbers. Those come in handy. And we have, I have the elements usually on. Here in the last one, the drop-down menu, you can toggle between different load cases. So here you can see the self-weight load case. The deflection plot would be exactly the same for both, but you can see the reaction changing. And when you select all, it just combines them linearly. So another handy component for post-processing beams is the beam viewer, so results beam view. And again, as with all the other ones, we plug in the model output into the model input. And then we start visualizing things. So at the moment we have, this is a one-to-one sort of fleshed cross-section, just showing us the cross-sections that I have selected. So if you change the cross-section down here in this part, so if I choose another index here, it would change, you would redraw it. You can choose the displacement in the bottom tab, so this toggle button here, displacement, shows us the amount of displacement. Of course, this is a contour plot, but without a legend, so we need a legend for it. So if you just double click in the canvas and type in legend, you've got the built-in grasshopper legend. And conveniently, Karamba, this component of Karamba, has the legend's colors and tags set up, so you can just plug it in straight into a legend. And what you do next is you set up a rectangle, so you can see it in the model space. It's the other way around. But basically, this gives us I'll just make it a bit bigger so we can see properly. So this is our deflection contour plot with this corresponding legend. So you can see that our truss is deflecting 20 millimeters. 1.9 centimeters. It's using European units. If we also click on utilization, you start seeing the percentage utilization of the cross-sectional capacity for the internal forces that are currently in the model. So you can see that the top chord is working at 19% and the bottom chord is working at 15%, and the two middle diagonals shouldn't be working at all. They're zero force elements. For symmetrical load case, of course. So one thing to bear in mind with this utilization here is the fact that this utilization is only based on this cross-sectional stress divided by the capacity. So it doesn't check buckling. It could be misleading. And for slender elements, it obviously is not conservative and not safe. So another thing we have here is the axial stress. So this is a cross-sectional stress in kilonewtons per centimeter squared. Again, European units. So this is quite handy. I mean, this is quite good for report generation, not necessarily for taking the forces out into Excel or anything like this. Or continuing to post-process the actual data from the model. This is good for just visualizing and checking your model and perhaps putting the results in a report. So another component that's handy for post-processing beam elements, and this is when you need the data, and almost always you need the data. So in results, beam resultant forces, there is a component called beam resultant forces. Just drag the model input in as before. In the inputs for this component, you can limit what you see. So you can limit it to a certain beam ID. So for example, if I only want to know what the force in the verticals is, I can type that in. And if I want to know what that is for my load case 1, which was the live load, I can plug that in, and it tells me that that's a list of axial forces. Actually, what's interesting about this version of Karamba is that we have a couple of components here in the results missing, which one of them is the beam forces and the beam displacements. And what I'm just showing you here is the beam resultant force, which is the maximum resultant section force for all the beams in the model. So that if you actually look at the resultant moments, then clearly that's not quite right, because it gives me one resultant per element. So in the full version, let's say that we're going to have two shears, an axial force, and two moments and one torsion. So there's 6 outputs for each element, and we'll be able to see that separately. And again, in a very similar, I mean, the component is exactly the same. It's just the outputs are not sort of made resultant. I think, as far as post-processing goes, probably, I think without the full version I won't be able to show you everything. So I'm going to plug in my laptop and show you all this other stuff. But you're going to have to bear with us to to fix the version so you can do it in your own time. So plugged in.